right, good evening. Thank you. So I'm going to start out with two apologies. This is actually an excerpt of a talk that I had intended to give in August, but unfortunately I suffered a grievous and debilitating injury the night before I was supposed to give it, so I had to cancel. So maybe some of you remember that late cancellation that occurred just a few months ago. And then the second is, I'm sorry for this title. I have no idea. I don't know what happened to me. I was considering coordinated omission, WTF, but no. Anyways, it's not very descriptive, so we'll jump into it. Little something about me. Should you happen to arrive at my front door at Halloween, that's what you're likely to encounter. But I've had a kind of long and varied career in a bunch of different things. My most, previous to this job with Azul Systems, I worked at Oracle in JVM engineering, fixing bugs in JRocket and Hotspot. And I've had kind of a wacky career in a whole bunch of different functional areas, research, applied research, engineering, did a stint in sales for a while, and I'm now in field engineering for Azul Systems. So, coordinated omission actually describes an error that we make when we're measuring latency. So we'll start out by talking about latency and what it is and why we measure it, and then we'll get into coordinated omission. So latency, very, very simple sort of common language definition. It's the amount of time it takes for an operation to complete from the point of view of the requesting entity, whatever that is. Each operation occurrence has its own measurement. We tend to look at groups or collections of these measurements and try and characterize that group. And that characterization tends to be a lot more complicated than just a single number. So very often in some statistical measurements we talk about means, averages, standard deviations, and so on. Latency measurements tend to be much more complicated than that. So we talk about percentiles, and we have 50th percentiles, and 90th percentiles, and 99th percentiles. And those are measures or indicators of how bad things get in the extreme worst cases. And this is why we measure latency, because we want to know how fast we can go, how much we can load our equipment, and as we load our equipment, as we load our software systems, they start behaving worse and worse and worse until finally something positively catastrophic occurs. And so this is what we're trying to avoid. We want to know how fast we can go without the whole system folding up and going over. Here are some of the other things that we use latency for. For sizing systems, how many servers do we need? How many cores do we need? How much memory do we need? And we do this by measuring latency on our systems, finding out when it's acceptable, when it's not, and then engineering that backwards into our requirements. Monitoring systems, see how they're behaving as they're running. Comparing one release to another, for example, to see if we have a performance regression. Qualifying new software or new systems or new approaches, new architectures to see if they're doing what we need. And then finally limiting, as we have load coming in from the outside world, we can partition that load in such a way that latency is managed on each of the components that handle it. So this is where we get into coordinated omission, and this is our CTO's funny slide. Basically, if you're involved in performance engineering or performance measurement, you probably have some ideas about the way things are supposed to be done. And if you want to stay in that world, then you take the blue pill, ignore everything I'm about to say, and your life will be fine, maybe. Or we can take the red pill and we'll take it, I mean, you're here, you may as well, right? So let's take the red pill and we'll see what coordinated omission actually is. So as I said earlier, coordinated omission is actually a very subtle way that we mismeasure performance, in particular mismeasure latency, and it can have some profound impacts on the way our systems behave. So let's just take a look at this for a minute, and this will start the audience participation part. So what we have here, this is a method that's testing a target, T, and we have a timer that's going off at a periodic rate every 10 milliseconds or something. And every 10 milliseconds, it's sending a probe to T, right there in the middle of the slide, T send probe. So we want to know how long these operations are taking. This is a classical measurement approach, right? We send probes regularly, periodically, test some representative operation on the system that we're testing from this external testing framework. We check the time at the beginning, check the time at the end, subtract them, and log, somehow put this into our statistics package, which we're going to look at later on. Okay? Pretty straightforward. So who can tell me what's wrong with this?
You're not always guaranteed to have the processor all the time, so your things might be delayed between the start and the stop, or the probe ending and the end time marking.
Yes, right, exactly. So if your operation time takes longer than the interval between your probes, then the frequency of your probes has adjusted. And this is one example of what we call coordinated omission. Now, if your test interval is 10 milliseconds and you're delayed to 11 milliseconds, well, that's not a big deal. But what we see in practice in real world systems, when we're firing off 10 millisecond probes, and suddenly the system stops for, say, 1,000 milliseconds or 13,000 milliseconds. We've seen delays like this in terms of seconds. Then you've missed a whole bunch of 10 millisecond samples. So when you take all your data that you put into your statistical logger, there's a whole bunch of data that's missing. There's a whole bunch of probes that never actually were sent. So your data is skewed badly and skewed optimistically. Your system looks like it's behaving a lot better than it really is. So, the root cause of this is that single-threaded external probe loop, which can't react to the fact that the system has paused. So that's one type of coordinated omission. Call it external coordinated omission, where an external framework is firing requests at our system under test. So how about this one? This is a more internal kind of test. So this should look pretty familiar. This is the standard HTTP servlet API that's part of Java EE servlet container everywhere. So basically, HTTP requests will come in. They'll come through this service method. From there, they get dispatched out to either the puts and gets and posts and so on. So what we do is we simply bracket this with our time capture the time at the beginning, service the request, capture the time at the end, and again, log the thing. Anybody see a problem here?
Network latency.
Okay, good example. He said network latency. All right. So here's a summary of what we're doing. The problem is that we miss things that are happening outside of our measured interval, things that occur before or after we actually get into that service code. So container delays, network stack, garbage collection in Java, which can pause things. So the analogy that we like to use is this kind of coffee shop. So what we're actually doing in that previous code example is we're measuring the time that a person is actually at the cash register, which let's call that the service time. The actual response time that we're truly interested in is how long it takes the person from the back of the line to get to the register, get their coffee, and then be done. So suppose we're measuring, for example, taking measurements of the time a person arrives at the cash register and the time they depart from the cash register. And the guy behind the cash register takes a 15-minute break. So that's one measurement that's really, really bad. And everybody else, so he comes back from break and he starts hustling, and everybody else in line gets reasonable response, right? So when we look at our statistics, we've got one really, really bad one and a whole bunch of reasonable ones. But that's not what really happened. So what the mistake we're making is we're confusing a service time as a response time. We think that the service time is actually the whole thing. So that's another example of coordinated omission. So here are the two examples, or the two kinds that we just talked about, sort of internal and external coordinated omission. And so you're probably scratching your heads and going, okay, big deal. What does this really affect anybody? Well, it's actually more common than you think. So a whole bunch of tools that are out there in the Java world actually make this mistake. JMeter is just one of many. The Cassandra response time measurement toolbox that's built into Cassandra also makes the same thing, and we've fed that information back to Cassandra people and to data stacks, and so far it hasn't been changed as of 3.0. So anyways, it's a subtle and very widespread thing. The difference it can make is these kinds of issues. So when you actually plot out your response times and plot them by histograms, you can see there's a very significant difference between what you measure when you're participating in this conspiracy of coordinated omission and what you actually get when you adjust for that. And it tends to get worse as load gets higher, as you might expect. So here, this blue line, this uncorrected data, we can look at that and we can say, well, that's meeting all of our service level agreement requirements, but in actuality, we're way outside of that. So does that really matter in the real world? Is the 99th percentile, which is sort of the benchmark that a lot of people use, as long as 99th percentile is good, then our system is behaving well, right? It's a very common sort of place to look. Here, so just from the world of HTTP page fills, here's the number of requests that a bunch of different well-known websites actually emit when you just navigate to their front page. The one I found interesting is Google.com. The simple Google page actually generates 31 HTTP requests just to get that simple search bar. So then if you do the math, the statistical math, what is the likelihood that just in that one page load, you're going to hit that 99th percentile behavior or worse? So Amazon.com, at least one of those HTTP requests is going to be 99th percentile or worse. 85% probability of that happening. CNN.com, and so on. So if your 99th percentile is in the several seconds range, that means that you can paint this whole page up there, and you can be waiting several seconds for important information. We actually had a customer who was a major retailer, and they would paint up this whole page, and the last thing that they painted was the price for the item that was being displayed. And occasionally they'd run into this issue where suddenly customers sitting there, they're looking at this thing and there's no price, just a gray rectangle. Anyways, so it can cause problems. So putting this into some more mathematical perspective, typical user session, 5-page loads, 40 resources or 40 requests per page. How many users will not experience something worse than the 95th percentile? A very small number. So we're actually hitting this, what we consider to be our worst case behavior, we're hitting it very frequently. And then how many users will experience at least one response that is longer than the 99.9th percentile? almost 1 in 5. So these behaviors that we consider abnormal and terrible and catastrophic are actually happening a lot more frequently than we think they are, and coordinated omission makes that issue worse. So what do we do with that? Well, there's a couple things you can do to help that. There's some measurement tools that can help. Hdr Histogram, if you've ever used it, is a nice, inside Java environment, a nice zero garbage way of collecting data that not only is zero garbage, but also has a large range. So because latencies can vary by several orders of magnitude, you need a way of capturing that and capturing it rather precisely. So Hdr Histogram has dynamic range and resolution. jHiccup is an agent that injects right into your Java application and measures pauses in Java execution. So as your JVM is executing and your application is executing as part of that, jHiccup will actually measure the number of times that the JVM completely stops, where no application work is happening at all. It's invisible to a lot of other monitoring tools, App Dynamics, trying to think of the other one. Anyways, typically when you're measuring performance of a Java application, you're measuring the amount of execution time spent in particular methods, hot methods, but this information is completely missed. So jHiccup is another interesting tool. A blatant plug for our product, the Zing JVM, which actually has a proprietary and patented garbage collector, which is pauseless. So garbage collection, which is a major cause of those JVM execution interruptions, is eliminated. We can handle very large heaps, all the way up to 2 terabytes in a single JVM. Here's some of the applications where Zing is particularly good. We've seen 20x improvements in Cassandra response times. The human response times, like feeding web pages, is another place where we're particularly good. So here's a couple of examples. So we're clocking ourselves at an 8 gigabyte heap, same application, and you can see the spikes that are occurring in hotspot going up to 14 seconds, 14,000 milliseconds. And in Zing, our worst case is 20 milliseconds, so you actually plot that with the ranges equal, then we get our flat line. We see this a lot. Here's another one, low latency trading application. That's one of our primary market areas is financial services. And so we see hotspot over here. 15 milliseconds in trading application is an eternity. Most trades are made within a millisecond. So over on the right is the Zing responses, and our worst case is a millisecond and a half. So, wrapping the whole thing up. So that's coordinated omission. It's actually one of several latency mismeasurements that we talk about in the bigger presentation, but wanted to bring that to you tonight. And here's a couple of tools you can use. Check out our website. Check out Zing JVM if you're in that kind of position. We have a free trial from the website. You can just sign up and download it. And let's see. So 95th and 99th percentiles happen much more frequently than we think they do. We talked about the way they cumulatively add up to each other. Coordinated omission is easy to miss as you're coding and creating measurement systems. So watch for that. And then finally, check out Zing if you get a chance. That's it. Thank you.